Okay, now there are some cases where we want to study an oxidation or reduction reaction, but it isn't that of a metal. So for example, we might have the reaction, like in this one here, we've got a reaction where hydrogen is reacting to produce H plus and 2 electrons. Now in this case, H2 or H plus couldn't act as an electrode. So if we want to study an oxidation or reduction reaction that is in solution or involves gases, what we use is what's called an inert electrode. And so platinum or graphite are used as electrodes in those cases. Okay, so they won't interact, but they will allow the oxidation or reduction to occur at their surface. Now, what we're going to do for the rest of the lesson is look at what's called cell voltage. And when we're studying a galvanic cell, we've got electrons flowing from the anode to the cathode. And the reason that electrons flow in that way from the anode to the cathode is because there's a difference in the electrical potential energy between the electrodes. So much like water will fall down a hill, the electrons will travel from a higher potential energy to a lower potential energy at the cathode. And the cell potential is actually the difference between the two. So the final position is the cathode and the initial position is the anode. So if we want to find the cell potential change, what we're going to end up doing is taking the potential at the cathode and we're going to subtract the potential at the anode. So this is going to be a key formula for the remainder of this lesson. Now, the difficulty that we have is that we can't actually determine the cell potential of a half cell. So I can't just measure on its own the potential of zinc to gain or lose electrons. So what we need to do is use what are called standard reduction potentials. Okay. When we do a standard reduction potential, what we are doing is we are comparing everything's ability to gain electrons to a standard. And the standard electrode that we examine is called the She electrode, the standard hydrogen electrode. And what we've done is we've assigned this potential to be 0. And we compare everything else relative to this standard hydrogen electrode. So this is the standard hydrogen electrode here. The reduction reaction that would occur is the H plus gaining electrons to form hydrogen. So this is the example where we would need an inert electrode. So we use a platinum electrode, and what we do is we've got a hydrochloric acid solution, and we bubble hydrogen gas through here. Okay, so much like in all the other scenarios, we've got both substances available in the half cell. Okay, so this would be how we look at it as an oxidation, and this is what would occur if it was a reduction reaction. Now we've assigned this to have a potential of 0, and we've used it to create a table of standard reduction potentials. And the way that we've done that is by putting everything relative to this particular cell. Okay? So for example, if I want to know what the relative potential of zinc is, I place it up against the She electrode and I measure the voltage, the cell voltage, which is measuring the difference in potential between these 2 points. Because I've assigned this to be 0, I am then able to determine what the relative potential of the zinc is compared to the She electrode. So when we read the voltage, that's not all the information we need. We actually need to examine the cell to determine what is the anode and what is the cathode of this cell connected to the She electrode. So when we connect the zinc, we read that the overall cell voltage is 0.76. But how we decide which one is the anode and which one is the cathode is by examining the actual substances. And we monitor the mass of the zinc in this case. In this case, the zinc actually decreases in mass. So we know that it is being oxidized, that the zinc electrode is losing electrons to form Zn2+. So I now know that zinc is the anode and the She electrode is the cathode. So these are the reactions that are happening in this galvanic cell with an overall cell potential of 0.76. So as I said before, to determine the E cell, we need to take the reduction potential of the cathode and we need to subtract the reduction potential of the anode. So in this case, I know the overall cell potential is 0.76. I know the cell potential of the cathode is 0 because I've assigned it to be that. So I can find the cell potential of the anode, and it is measured to be 0.76. So if you look ahead in your notes to page 18, you can see the table of standard reduction potentials. If you look at the numbers, you can see it starts with positives, and then there's the 0 point, and that's where the hydrogen reduction reaction is. And if you continue along and see the zinc reduction reaction, you'll see that its reduction potential is minus 0.76 volts. Okay, so let's look at another example here. We've got another situation where we've got the She electrode connected to another half cell, in this case the copper reaction. So we've got a copper electrode in a copper solution. The information that we're given is that the mass of the copper is increasing, and it gives us the voltage to be 0.34. So what we need to determine is which one is the anode and which one is the cathode. Because the mass of the copper is increasing, we know that it must be the cathode, because the copper ions are gaining electrons to form copper on the surface of the electrode, and therefore it's increasing. So to draw the cell diagram for this, we know that the anode is the She electrode. We use an inert electrode of platinum. And then we've got H plus and H2, and we're always going to assume standard states unless we are otherwise told. We connect using a salt bridge to the copper solution, and we've got a copper electrode. Okay, so that is the appropriate cell diagram. For the half reactions, okay, we know at the cathode that the copper is gaining electrons, okay, to form copper. And in this case, the She electrode is undergoing oxidation, so the oxidation reaction for that is the hydrogen gas is being oxidized to hydrogen ions. Okay, so these are the two half reactions that are occurring in this cell. To determine the standard reduction potential of copper, we know that E of the cell is equal to the reduction potential at the cathode minus the reduction potential at the anode. Okay, we know the overall cell voltage is 0.34, and we know that the copper is the cathode and that the anode or the She electrode has 0 volts. So in this case, the reduction potential at the cathode is 0.34 volts. The last question is to determine the EMF of the Daniell cell. EMF stands for electromotive force, and it's important that you understand that when you're asked for electromotive force, you're simply being asked for the voltage of the cell, or the cell voltage. So if we want the cell voltage, it is the reduction potential of the cathode minus the reduction potential of the anode. And the Daniell cell, recall, is the one involving zinc and copper. And in the reaction with zinc and copper, the cathode is the copper, and the anode is the zinc. So we take the reduction potential at the cathode of 0.34 and we subtract the reduction potential at the anode of 0.76. And in this case, we get a voltage of 1.10. Now for galvanic cells, we've said that they are spontaneous reactions. The E cell for a spontaneous reaction is greater than 0, okay, as is the case with the zinc-copper reaction. Okay. Now there's just a few things to note about the table of standard reduction potentials. So as we look at the table here, there's a few things. First of all of the reactions are red in the forward direction and they're all reduction reactions. So in a lot of cases, you'll need to flip the reaction around to determine what the oxidation reaction is. This series is in line with the activity series, and the metals are in the same order on this as they would be on the activity series. So you can see lithium is very likely, it's at the bottom here, so it's very unlikely to gain electrons. Okay, fluorine is at the top of the list here. It's really likely to gain electrons. So the activity series really only showed the metal reactions, but you'll see this is a more complete list and has a variety of other redox reactions of concern, okay, involving gases or solutions like permanganate and nitrates and sulfates, okay, that are useful to us. Okay, so the more positive the reduction potential, the more likely a substance is to be reduced. So the more likely it's going to be an oxidizing agent. And the reverse is true. If you've got a highly negative cell potential, it's going to be very likely to lose electrons instead, and therefore it's a very strong reducing agent. Now, one thing that's important to note is that the stoichiometric coefficients don't affect the cell potential. So when you multiply a reaction by 2 or 3 in order to ensure that the electrons transferred in a reaction are equal, okay, they do not affect the cell potential. It's called an intensive property, so it's kind of like temperature. It doesn't matter the amount of water you have, the boiling point of water is the same. Okay, or density, doesn't matter how much water you have, the density of water is the same throughout. Okay, so those are just some key features of the standard reduction potential chart. Okay. One other thing to note here, if we look at the zinc and the copper, much like the activity series, can be used to determine what will happen in a particular reaction. Okay. The one that is higher up on the list is more likely to be reduced, okay, which makes sense based on our discussion of it's more likely to be reduced on the top versus on the bottom. One thing to be careful of is that you want to really look carefully at the charges on the ions to make sure that you're selecting the right one. Okay, so for copper, Cu2 plus 2 electrons going to copper is different from copper just gaining 1 electron to form a copper ion. Okay, so just be mindful of that while you're using the table.